Hi, and welcome to the lecture on generalized linear models. In this lecture, we're going to change gears quite a bit and switch from linear additive response models to the much broader class of generalized linear models. These models take care of some instances that linear models might struggle with, but maybe at the expense of some of the nicety and the mathematical neatness that exist for linear models. Before I begin talking about generalized linear models, I'd like to review a little bit about linear models and maybe some of their benefits and tough spots. So, to me, the linear model is the single most useful applied statistical technique. But again, they're not without their limitations. The assumption of additivity is one that is kind of hard to apply when you have, for example, binary data. It's weird to think of binary data as being additive. The error structure would have to be kind of weird in that case. In addition, if your data is strictly positive, then having additive Gaussian errors presents a problem because that allows for positive mass on negative values. Now that may not be a problem, and I often say that it's not a problem to have strictly positive data where the errors look Gaussian and there's just very low probability down towards negative values. That's often okay. But on the other hand, if the normal distribution is putting a lot of positive probability on negative values, even though you know your response has to be positive, then that's problematic for your model. On the other hand, you might try transformation. Common transformation when your outcome has to be strictly positive is to take the natural log of it. Natural log is, to me, in my mind, perhaps the most interpretable transformation possible. Putting that one to the side, lots of other transformations that are available to try to make our data more normal, such as for binomial data, people often will take a so-called arcsine square root transformation. That often destroys a large amount of interpretability of our model coefficients, which is a real problem. The log transformation, I would say, is in a class of its own, and in many ways can make the coefficients more interpretable. So we'll discuss that separately. There's another reason to perhaps approach generalized linear models rather than doing a transformation of the outcome or to approximate things with a linear model it's just nice and pleasant to have a model on the scale in which the data was recorded without having a transformation, and that really honors the assumption, the known assumptions about the data. So if we have binary data, a model that really honors the fact that the data is binary, and really doesn't require us to transform it, it has a lot of kind of pleasantness to it, and it sort of makes a lot of internal sense. And then I mentioned here on this last point the natural log transformation, which is probably the most common transformation, isn't applicable for negative or zero values. Now there's some fixes for that, but then that harms some of the nice properties of that transformation, some of the really nice interpretable properties. So generalized linear models were from a 1972 paper by Nelder and Wedderburn, a kind of famous paper that if you are a PhD statistician, you've for certain read. And a generalized linear model has three components. First of all, the distribution that describes the randomness has to come from a particular family of distributions called an exponential family. This is a large family of distributions that includes things like the normal and the binomial and the Poisson. So that's the random component, right? That's the exponential family is the random component. Then the systematic component is the so-called linear predictor. That's the part that we're modeling. And we've done this very much so in linear models already. The random component was the errors, the systematic component was the linear component with the regression, covariates and coefficients. And then we need some way to connect the two, and the link function, it connects some important mean from the exponential family distribution to the linear predictor. So there's three things that we need. We need the distribution, which is going to be an exponential family for a generalized linear model. We need the systematic component, which think of this as the linear predictor. We think of this as the set of regression variables and coefficients. And then we need a link function that links the two. Okay, so let's try an example. And we'll go to our most familiar example, which is linear models, the subject that we've been covering the entire class up to this point. So in this case, we're assuming that our y is normal with a mean mu I and variance sigma squared, and this happens to be an exponential family distribution. And then we're going to define the linear predictor, this eta I, okay, to be the collection of covariates, x's, times their coefficients, beta. Okay? And in this case, our link function is just going to be the identity link function. It just says that the mu from the normal distribution is exactly this collection, this sum of covariates and coefficients. And so this just leads the same model that we've been talking about all along. We could just write it instead as yi is equal to the mu component, which is summation xi beta, plus the error component. So we've simply written out the linear model in a separate way. We've talked about the fact, instead of saying that the errors are normally distributed, we say the y is normally distributed, which is a consequence of our other specification. We specify a linear predictor kind of separately, okay, and then we just connect the mean from the normal distribution to the linear predictor. And you might think this seems like a crazy thing to do when just writing it out as an additive sum with additive errors seems like such an easy thing to do. But as we move over to different settings like the Poisson and the binomial setting, it'll be quite a bit more apparent why we're doing this. So let's take, in my mind, perhaps the most useful variation of generalized linear models, logistic regression. So in this setting, we have data that are 0, 1, so binary. And so it doesn't make a lot of sense to assume they come from a normal distribution. So the the only distribution available to us for coin flips for 0, 1 outcomes is the so-called Bernoulli distribution. So we're going to assume that our data, our outcome y's, follow a Bernoulli distribution where the probability of a head, or the so-called expected value of the y, is mu I. Okay, so we're assuming these are we're modeling our data as if it's a bunch of coin flips, only the probability of a head may switch from flip to flip, and it's not necessarily 0.5. Okay, so the probability is given by this parameter mu sub I. The linear predictor is still the same. It's just the sum of the covariates times their coefficients. Now the link function in this case, the most famous and most common one, is the so-called logistic link function, or the log odds. And so in this case, the way in which we're going to get from the mean, from the probability of a head, to the linear predictor is to take the log of the odds. So the odds are the probability over 1 minus the probability. So in this case, we've written it as mu over 1 minus mu. And we're going to take the natural logarithm of it. So the logarithm, what that basically means is that we're going to transform our mean, our probability of getting ahead. We're going to transform it, and then on that transform scale is where the covariates and their coefficients, the kind of standard part of our linear model, is going to appear. So notice we're transforming the mean of the distribution. We're not transforming the y's themselves. Okay, right? That's a big distinction, and that's the neat part of generalized linear models. What we're transforming, we're assuming that the coin has a probability of a head. We're modeling our data as if it's a coin. That coin has the probability of getting a head, and that probability, if we transform it in a specific way, then it relates to our covariates and coefficients. Okay, so we can go backwards from the log odds to go to get back to the mean itself. Okay, and so the inverse logit, I guess I often call that the xbit, though I don't know how standard that is e to the eta I over 1 plus e to the eta I, and that gets you back to mu. Okay, so going forward, take log of mu over 1 minus mu, that gives us eta, If we take e to the eta over 1 plus e to the eta, that gets us back to mu. And by the way, 1 minus mu, the probability of a tail, is 1 over e to the eta. So we could write out our likelihood as the binomial likelihood right there like this. And I think you can see then, well, it's through this function, through this likelihood, like we've talked about in our stat inference class. It's through that likelihood that we're going to optimize, we're going to maximize that likelihood to obtain our parameter estimates. Okay, let's go through another example, Poisson regression. Or I like to say Poisson regression. I know I'm not pronouncing it correctly, but I like to say it that way. So assume that y is Poisson mu I, where the mu I is the expected value of each of the Poisson random variables. In this case, the mu has to be larger than 0. So Poisson is extremely useful for modeling count data, or that's really what it's for. It's for modeling counts. So if you have a bunch of positive counts that are unbounded, right? So not like binomial counts where they're bounded by the number of coin flips you take. Poisson counts are unbounded. And so it's a very useful model. Let's suppose you want to count the number of people that show up at a bus stop. You don't have an upper limit on that, or sure, there is some upper limit, but you don't really know what it is. So you might want to model that as Poisson. Our link function, again, our linear predictor is, again, the same as it was in every case. It's just the sum of the covariates times their coefficients. The link function in this case is the log link. The most common link function for the Poisson case is the log link. So, and remember, so we go from the mean, mu, to the linear predictor, eta, by taking the log of the mean. Okay, so again, we're not logging the data, we're logging the mean from the distribution that the data is assumed to come from. And then remember, the inverse of the natural logarithm is e to that thing. So we can go backwards from eta back to mu by taking e to the eta. So by doing that, we can just simply write out what our likelihood is. And again, the way GLMs work is they obtain the parameter estimates by maximizing the likelihood. So I give some technical facts here, and it basically we're just saying that the likelihood simplifies quite a bit in all these cases because of the particular link function that we've shown. But I want to point out this final point here, which says that the maximum likelihood looks like a kind of sort of like an equation that we would want to solve, not unlike least squares. So think way back to our initial lectures on least squares. We found our estimates by minimizing the sum of the squared vertical distances between the fitted line and the outcome. Well, if you wanted to opt to minimize that function in a sort of automatic way, you might take a derivative. So then that function would no longer be squared, the 2 would come down. And so you get to try to find the root of that derivative, you just get a linear equation. Well, this generalization in generalized linear models, by solving the likelihood, trying to maximize the likelihood, you get a very similar equation that you want to set equal to 0 and solve that gives you your estimates. And I give it right here. And it's basically not very similar to the linear model case, only there's a set of weights and a variance in the denominator that kind of doesn't go away like it does in the least squares case. So again, this is not for this class. It's just if you're interested in some of the details of the fitting. Basically, the point of this slide is to say that it's very similar to what's going on in least squares. Just how we get to that point is a little bit more circuitous. For most people in most settings, this is all going to be very transparent to you. You're going to mostly concern yourself with the interpretation of your generalized linear model. You're not going to concern yourself too much with the specifics of how it was fit. There is an important point I'd like to note about generalized linear models, especially for some of the cases like the Poisson case and the binomial case. For the linear model, remember we had this assumption of a constant variance. However, for the Bernoulli case, remember the variance of a coin flip is p times 1 minus p. And in the notation we're giving here, it's mu times 1 minus mu. But remember, our mu depends on I. So what we're saying is the variance actually depends on which observation you're looking at. The same, unlike the linear model case where the variance is constant across I. Same thing in the Poisson case. So the variance of a Poisson is its mean, and so in this case the Poisson has a variance that differs by I. Now this is a modeling assumption that you can check, right? So if you have Poisson data, you can, let's say you have several Poisson observations at the same level of covariance, so the mean should be the same, then the variance of those should be roughly equal to the mean, and if your data doesn't exhibit that, then that's a problem. So this is a highly consistent, this is an important consideration, important practical consideration in generalized linear models, is that the modeling assumptions often put a restriction on a relationship between the mean and the variance, and that relationship may not hold in your specific data set. So what can you do? Well, there was a way to address this by having a more flexible variance model, even though you lose some of the assumptions of generalized linear models. And these are all standard options in R, and so all you look at are so-called quasi-blank options in the family, in the distribution. So we're going to go through lots of examples, but the point is that's, so if you see in R that you see that you can fit a model that's Poisson with its GLM function, but then you see there's another option called quasi-Poisson. The same thing with binomial. You can see an option where you fit binomial, but then you see another option where it's quasi-binomial. What that's referring to is a slightly more flexible variance model in case your data doesn't adhere to the GLM variance structure. Okay? And so these are all standard options, in every statistical language that fits GLMs also automatically will fit these quasi-versions of GLMs with a more flexible variance structure. And I actually give the equation that it's trying to solve in order to get the fancier, more flexible variance structure. So just some odds and ends about the fitting before we go through the specific cases. We're going to do separately the Poisson case and the binomial case. We're not going to go through a full treatment of GLMs, just Poisson and binomial. But these equations have to be solved iteratively, so unlike the linear model, where you can just do strict linear algebra to find solutions, GLMs actually have to be optimized, which means sometimes the program fails. For example, if you have a lot of zeros in a binary regression, or zeros or ones, these things can happen. But other than that, then I think most of the analysis should be pretty familiar to us. If we want to get our predicted response, we're just going to take our coefficients, our estimated coefficients beta hat, multiply them times our regressors, and that will give us our predicted response. Now, notice this is going to be on the logit scale if you're doing, for example, logistic regression, or the log scale if you're doing Poisson regression. So you'll have to convert it back to the natural scale if you want it to be on the same scale as the original data. So if you're modeling coin flips and you get your coefficients and your regression coefficients and out, and you come up with predicted response, those will be on the logit scale. And if you want them to be back on the scale of the coin flip, the 0 or 1, between 0 or 1, you're going to need to take an inverse logit. And again, we're going to go through a lot of examples. I just want to outline these facts before we do the examples. The coefficients are interpreted very similarly to the way that our coefficients were interpreted in linear regression. They're the expected change in the change in the expected response per unit change in the regressors, holding the other regressors constant. The only difference is now this interpretation is done on the scale of the linear predictor. So in the binomial case, it's on the scale of the logit. On the Poisson case, it's on the scale of the log mean, and so on. So it's a slightly more complicated interpretation, but again, we are gaining the benefit of modeling our data naturally on its own scale, and we haven't had to transform the outcome at all. So the inference, we also lose the nice collection of closed form normal inferences that you get. We don't get t distributions anymore. We don't, and so, but largely this is transparent. There's a body of mathematics that has where statisticians and mathematicians have figured out what the right distributions are to compare all the coefficients and from the output of your GLM to, in order to get things like the p-values. And all of those are going to be tested. Our hypothesis tests for the coefficients are just going to be tested and interpreted in the same way as in our linear regression. Just the background that's going on is a little bit harder. One thing I would say, though, is all of these results are based on asymptotics, which means that they require larger sample sizes. So if you have a GLM setting with a very small sample size, then it's possible that things like your p-values aren't really applicable. And so many of the ideas can be brought over from GLMs. So this was just a whirlwind overview of GLMs. Now, for the next two lectures, let's just dig into the two most important cases of binomial and Bernoulli regression via logistic regression and Poisson regression. So we're going to spend a lot of time with those, and then if you want further material on GLMs, there's some more advanced classes that you can take. Okay, well, thank you for attending this lecture, and I look forward to seeing you in the next one, where we're going to cover logistic regression for binary outcomes.